Hi everyone, welcome to back to channel. Today we are diving into the one of the fundamental concept in automatic theory, conversion and NFA. It is explained non-deterministic finite automaton into 2DFA. They explain deterministic finite automaton. If you are into computer science, you will know this a key topic for understanding how machines process language. So let's break it down in a super simple way. Yes, this is homework 2 and I'm Aşk İsmail Çevikbay. Yes, I'm reading this homework. Question 1 is convert the NFA into a DFA. Yes, 0, 1, 0, 1, and go on to 0 and complete it. Alright, so we have got this NFA right here. What we want to do is turn this into a DFA, and we will use a method called subset construction to do that. Sounds fancy, but it's really not as complicated as it seems. Let me walk you through the steps. And step 1, identify start state. First up, we'll look at the start state of the NFA. In this case, it is a state 1. Now in the DFA, our start state will be the set that contains state 1. So our initial DFA state is going to be is 1. Step 2, find the transition. Now we need to expand this state by looking at where it can go. We will do this for each input symbol in alphabet. And each time we move, we will form a new set of states. For example, from state 1, if we read a 0, we can move the states 1 and 2. So the DFA's new state becomes 1 or 2. For 1, we move the state 2. So 2 become a new state. Then we repeat this for each of the new states or states we create. So from 2, if we read 0, we move to state 3. And if we read a 1, we stay in state 2. Yes, I'm explaining this step. And step 3, eliminate redundancies. Once we have covered all transition, we will check for duplicate set. We only want unique use set in our DFA, so we'll remove any duplicates. In our case, there are no duplicates, so we keep going. And step 4, define except states. Next, we identify the except states in NFA. Our except states was state 3, right? So in DFA, instead set that contains state 3 will also be an except state. For us, that is the state 3. And step 5, the final DFA. Finally, we can now the draft DFA. Yes, I'm skipping these NFA for the DFA. Finally, we can now the draft the DFA. Here's what we end up. It is got 3 states, 1, 1, 2, 2, and 3. We also have the transition clearly defined for each input symbol. The sum it up, we have converted our NFA into a deterministic version. The DFA, we still accept the same launch, but now works without any ambiguity. And that it is. That's how we convert NFA to a DFA. It's a little bit of a theory and logic, but once you break it down into steps, it becomes super manageable. If you found this helpful, you go to your write it and write it. And I'm skip the question 2. Draw a finished state machine that accept the complement the launch accepted by the non-deterministic machine below. Yes, you see the move to 0 and next state and 0, 1 the end state go to and we are going to divide the finished state machine. specifically how to derive determinist definite automata that accept the complement of a given non-determinist definite automata. Stick around because I will break down step by step and simple and visual way. Let's get started. So here's the problem we are working on. We have been given a non-determinist definite automata that looks like this. The question is asking as I create a DFA that accepts the complement of the launch except by NFA. If you are not sure what the complement is, don't worry. I will explain everything in just a second. And step 1. Understanding the NFA. What is the NFA? First, let's take a closer look at this NFA. It has three states, Q0, Q1, and Q2. The start state is Q0 and the accepting state is Q2, indicated by the double circle. The NFA works like this. From the start state Q0, we move to state Q1 if the input is 0. From Q1, we can transition to accepting state Q2 if the input is either 0 or 1. So basically, this NFA accepts any strings that starts with a 0 and followed by any combination of zeros and ones. Got that? Awesome! Now let's talk about the complement. Yes, step 3. What is the complement? Now, when we talk about the complement of a launch, we mean all strings that are not accepted by original automaton. In this case, we want to design a DFA that accepts everything except the strings that the NFA accepts. So, if the NFA accepts strings like 0 or 01 or 00 and so on, or complement, DFA should accept all other strings. And step 3, converting the complement DFA. Yes, and step other page and step explanation. You write it, and this is conclusion. And step 3. Alright, now that we understand the NFA and the complement, let's go ahead and construct the DFA. We will use the same state, but we will two important things. Flip the acceptance state, it is the first. This state that was accepting in the NFA will now be non-accepting in the DFA. Likewise, non-accepting state in the NFA will become accepting in the DFA. And the second one is keep the transition the same, because we are only interested flipping the logic of which strings are accepted. Let's sketch out now. Yes, I'm skip the sketch. This is the sketch. And step 4, drawing the complement. In the complement DFA, Q0, yes, you know, you see in the Q0. Q0 will now be an accepting state because it was non-accepting in the NFA. And go on the 0, Q2, Q1. Q0 will now be an accepting state because it's non-accepting in the NFA. Q1 in a state non-accepting, and Q2 will now be a non-accepting state because it was accepting in the NFA. No, NFA. Yes. Also, the transitions stay the same from Q0 to Q1 on input to 0, from Q1 to Q0 on input to 0 or 1. Yes, it is the question 3. Yes, I'm write it question 3. Writing question 3. Prove that if L1 is regular and L2 is regular, then so is L1 or L2, the set of all string in the L1, but not in L2. Yes. We are diving into a super cool topic from automata theory again. We are going to prove that if two lines L1 and L2 are regular, then L1 minus L2, yes, this or and minus, I think minus, alright? Yes, also regular. So basically, if you take all the strings that are in L1 but not in L2, the set will still be regular. Let's break it down step by step. Yes. Alright, so first things first, what does it mean for a line to be regular? Well, regular lines are the ones that can be described with the finite automata. Those little machines with a limited numbers of states that help us recognize patterns in strings. Now let's say we have two regular lines, L1 and L2. These can both be recognized by their own finite automata. Let's call them A1 and A2. Our goal is to prove that L minus L2, which is the set of strings in L1 but not in L2, is also regular. So, how do we prove this? Here's the game plan. First, starts with two finite automata, A1 for L2 and A1 for L2. Since both L1 and L2 are regular, we know that A1 and A2 exist. And the second one, turn A2 into a machine that rejects L2. Why? Because we want to find strings that are in L1 but not in L2. We can do this by complementation. A2 is that means the flipping it's accepting and rejecting state. This new automaton will now accepted everything that's not in L2. And the third one, combine these two automata, A1 and the complemented A2, using the intersection operation. When we intersect A1, which accept L1, and the complemented A2, which accept everything outside of L2, we will be left with exactly what we want, strings that are in L1 but not in L2. And here's what. Regular lines are closed under the intersection, so this new line will also be regular. So here's final proof. We start and you see the proof. This is the mathematical solution, the proof outline. Yes, you see it. And the final proof. We start with two regular lines. We complement one of the automata to get all strings not in L2. We intersect two automata to get the L1 minus L2. Since regular lines are closed under this operation, L1 minus L2 is also regular. And there you have it. We have just shown that L1 minus L2, it is regular if both L1 and L2 are regular. It's a really net result that builds on the basic properties of finite automata. I hope this helped to clear things up. If you enjoyed this video, don't forget to like and my YouTube channel is liked. And skip the question 4. And I'm writing the question 4. Prove that if L is regular, then prefix L is regular. Prefix L, explain, is the set of all strings which are proper prefix of a string in L. And the answer is the next slide. Yeah, to prove that if L is regular line, then the set of all prefix of strings in L denoted by prefix L is also regular. We will use the following approach. And If a line L is regular, then prefix L is also regular. This means we are going to show that if we have a regular line, all the prefixes of strings in that line also from a regular line. Read the diamond. Let's go. Alright, first let's define what prefix L means. If you have a string in L says ABC, its prefix would be A, AB, and ABC. We want to collect all possible proper prefixes of L strings in L. So prefixes L is a set of these prefixes for every string in L. For example, if L has the strings ABC and def, DAF, it's the shortest one, def. Then prefix L would include A, AB, ABC, D, DE, DEF. Now the big question: if L is regular, does this mean prefix L is also regular? It is the short answer, yes, and we are going to prove it. So how to prove it? We will use finite automata because that's how we deal with regular lines. Here's the plan. The first one is start with a finite automaton A that recognizes the line L. Since L is regular, we know there is a finite automaton for it. Modify this automaton A to create a new automaton that recognizes all prefixes of strings in L. How to modify the automaton? Here's how we can do this step by step. The first one, create a new automaton. That's similar to A, but with a twist. In A, we have set an accepting state that tell us when we have read a string that belongs to L. Now, in our new automaton, we will allow the machine to accept not only the final state of A, but also at any point along the way. That way, the automaton can accept any prefix of a string in L. The second one, make all states accepting state. We will modify A so that every state is an accepting state. Why? Because a string might stop any point and still be prefix something in L. By making every state an accepting state, we ensure that all possible prefixes are accepted. Keep the transition the same. We will keep the same transition as in the original automaton A. So the structure of how we process the string remains intact. And that is what we've done is transform the original automaton for L into automaton that accept all the prefixes strings in L. Since this new automaton is a finite automaton, we have just shown that prefix L is regular because it can be recognized by this modified automaton. Excited looking at the camera. You don't see it, but I'm excited this concept. It is very awesome and amazing. Let's sum it up. We started with a regular line L, which has finite automaton. We modified the automaton so that it accepts not just complement string in L, but all the prefixes since the finite automaton recognize regular lines. Prefix L is also regular. This is a really cool result because it shows that regular lines are super flexible. They are closed under operation like defined prefixing. Thank you listening and seeing and bye bye next videos and for the next videos and bye bye.